Every single time you flip a light switch, you're actually tapping into this huge, century-old battle of ideas. So today, we're going to dig into alternating current. And we're not just talking about what it is, but the really cool story of why this specific type of electricity won the massive war to power our entire world.
See, the story of modern electricity, it's not just some dry science textbook stuff. It's actually this incredible tale of fierce rivalry, brilliant minds, and a truly revolutionary idea. And right at the heart of it all, you've got these two guys, inventor Nikola Tesla and the industrialist George Westinghouse. They were the ones who really championed a new and way better way to power the future. So they and their rivals, they were up against this absolutely monumental challenge. It wasn't enough to just make electricity. The real trick was getting that power from point A to point B, from the power plant to the people. So the huge question on everyone's mind was, how in the world do you efficiently send electrical energy across vast distances to light up entire cities and power massive industries?
And this challenge, well, it sparked what we now call the War of the Currents. And this was a super high-stakes battle. We're talking about two fundamentally different kinds of electricity going head-to-head, with literally the future of the modern world hanging in the balance. Okay, so on one side of this fight, you had the world-famous Thomas Edison, and he was all in on direct current, or DC. The easiest way to think about DC is like a river flowing steadily in just one direction. But then, on the other side, you had alternating current, or AC. This was the system backed by Tesla and Westinghouse. And with AC, the flow of electricity is constantly, and I mean rapidly, reversing direction. So yeah, unlike that steady march of DC, AC power kind of ebbs and flows, almost like a wave. Now, at first glance, all that changing direction, it might seem really inefficient, right? But here's the crazy part. As we're about to see, that constant change is the very thing that unlocks AC's greatest superpower. And that superpower is its ability to travel long, long distances. So the big question is, why did AC win this war? And not just win, but win so decisively. Well, the answer comes down to this one deceptively simple device that became its secret weapon. A little thing that completely changed the entire game when it came to the economics of electricity. And here it is. This is that secret weapon, the transformer. And when you look at it, it's really just two coils of wire wrapped around an iron core. But, and this is the magic part, through a principle called mutual induction, this simple little setup can change the voltage of an AC circuit with almost zero energy loss. It can step it way, way up or step it way back down. Okay, now this is the absolute key. Transformers only work with AC. That's it. Why? Because they need that changing magnetic field that AC's back and forth current creates. DC, with its steady, one-way flow, just makes a static magnetic field, and that does absolutely nothing in a transformer. This one single difference is what gave AC this massive, unbeatable advantage for building a power grid. So let me walk you through the journey your electricity takes. First, at the power plant, it gets stepped up to a crazy high voltage. This lets it travel super efficiently over power lines without losing much energy as heat. Then, right before it gets to your house, other transformers step it down to a safe, usable level. It's such an elegant system, and it's exactly why AC can power a whole country from just a few sources, something DC just couldn't dream of doing. All right, so let's go a little deeper here, because it's not just about the transformer. AC's whole back-and-forth nature means it interacts with electronic parts in some really interesting and, surprisingly useful ways that you just don't get with DC. So, in an AC circuit, you've got certain parts that don't just resist the current, they actually react to its constant changing. We call this reactance. You can kind of think of it as a special type of resistance that only pops up when the electricity is sloshing back and forth. And the two key players here are things called inductors and capacitors. So let's take an inductor first. It's really just a coil of wire. Now, as the AC current tries to rush back and forth through that coil, the coil creates a magnetic field that pushes back. It's like it's putting on the brakes, always fighting against the change. And what that does is it makes the current a little sluggish, so it ends up lagging behind the voltage. But then you have a capacitor. A capacitor's job is to store and release electrical charge. And with AC, the exact opposite thing happens. The capacitor charges up and discharges so fast that the current is actually rushing in and out ahead of the voltage changes. So in this case, the current leads the voltage. Okay, so you've got one thing that makes the current lag, and another that makes it lead. Now, this is where it gets really cool. What happens when you put both of them in the same AC circuit? Well, if you get it just right, so the lagging effect from the inductor and the leading effect from the capacitor are perfectly balanced, something pretty amazing happens.
And I'm not talking about some quirky physics thing that only matters in a lab. This is the fundamental principle that allows you to tune a radio. You ever wonder how your car radio can pick out that one station you want from a sea of dozens of other signals? This is it. This is the principle that basically unlocked the entire electromagnetic spectrum for communication.
To really get this, there's a perfect analogy. Think about pushing a kid on a swing. The swing has its own natural rhythm, right? If you push it just the right moment, every single time, each push adds a little more energy, and the swing goes higher and higher. But if you push at the wrong time, you just mess up the whole rhythm.
Well, that is exactly what resonance is in an electrical circuit. It's that one special frequency where the inductor's lagging effect and the capacitor's leading effect are perfectly equal, and they just cancel each other out. It's just like pushing that swing at its perfect natural frequency.
And at that one perfect frequency, because those lagging and leading effects cancel out, something incredible happens. The circuit's total opposition, its total resistance to that one frequency, drops to almost nothing. It's like you've just opened up a 10-lane superhighway for that one signal, letting it blast through at maximum strength, while all the other frequencies are stuck in bumper-to-bumper traffic.
So think about it. When you turn the dial on an old radio, what you're really doing is changing the capacitor inside the tuning circuit. And by doing that, you're changing the circuit's resonant frequency. As soon as you dial it in to match the frequency of the station you want to hear, boom, that signal becomes super strong, it comes blasting through your speakers, and all the others just get filtered out. It's that simple.
So yeah, from the massive power grid all the way down to the radio on your shelf, it's these unique properties of AC that really built the entire framework for our modern connected world. So when you put it all together, thanks to the insane efficiency of the transformer for sending power over long distances, and these really cool, useful properties of resonance that gave us things like radio, alternating current didn't just win that war. It literally went on to build the entire electrical world that we live in today.
But that leaves us with a final, kind of provocative thought. AC definitely built the 20th century grid, no question. But look around. Our modern world is absolutely filled with stuff that runs on DC. I'm talking about our laptops, our phones, solar panels, electric cars, the list goes on. So while AC is still the thing that delivers power to our homes, you have to wonder, is the war of the currents really over? Or are we maybe seeing the beginning of round two?